In this video, we are going to solve examples on Fourier transform and plot the spectrum for Fourier transform. To solve this example, first we have to write the equation for Fourier transform. So we know that for Fourier transform, x of omega is given as integration minus infinity to plus infinity x of t into e raised to minus j omega t dt. So we are supposed to add the value of x of t in this integration, which is given as e raised to minus at u of t, and simplify the integration to get x of omega. So here x of t is e raised to minus at into u of t with the basis function e raised to minus j omega t dt. But we know that u of t is our unit step signal, which is given as 1 for t greater than or equal to 0 and 0 for t less than 0. So unit step signal only exists for positive values of time and whose amplitude is 1, and for the negative values of time it is 0. So if we split up the above integration from minus infinity to 0, here it is e raised to minus at, the amplitude of u of t is 0 and the basis function e raised to minus j omega t dt plus integration from 0 to infinity e raised to minus at, u of t is 1 for the positive values of time and the basis function e raised to minus j omega t dt. So the first integration becomes 0 and we have to evaluate only the second integration. So here the second integration remains to be integration from 0 to infinity e raised to minus at into e raised to minus j omega t dt. So we have to simplify this equation and the first integration becomes 0. So here integration from 0 to infinity. So let us combine the exponential terms, so we can take minus sign common. Here remember, whenever you are simplifying the exponential and its power, always remember that the t term should be at last and the remaining term should be taken in the brackets. One more thing, whenever the integration of such exponential term, if the integration is from 0 to infinity, so here we have infinity term, positive infinity term in the integration limits. So in that case, always try to take negative sign common in the exponential. I will repeat it again. If in the integration we have the limit as positive infinity, then try to take negative sign common in the power of exponential. And if in the integration, if we have the limit as minus infinity, then try to take positive term common in this exponential. So this will help us in the next step where we can apply the upper limit minus lower limit and we can easily get the value. So here we have positive infinity in the integration, so I am going to take negative sign common. Now in the bracket, remaining term is a plus j omega, because we have taken minus sign common, and the remaining term is t. So we have represented this 2 exponential into a single exponential dt. So always try to simplify the exponential terms as shown over here, where sign is taken first, then in the brackets we have the remaining terms, and then after bracket we have t term. So now if we take its integration, we have e raised to minus a plus j omega into t divided by minus of a plus j omega with the limits 0 to infinity. Now we need to put up the limits, upper limit minus lower limit. So the first term e raised to minus t, which is infinity, so becomes e raised to minus infinity minus lower limit is 0. So e raised to 0 whole divided by minus of a plus j omega. So let us simplify it again. So we know that e raised to minus infinity is 0 and e raised to 0 is 1. So this equation becomes, so e raised to minus infinity is 0. So 0 minus 1 divided by minus of a plus j omega. So if we simplify it further, our x of omega is 1 upon a plus j omega. So this is the answer for frequency representation of given signal, which is e raised to minus at u of t. So this completes with the first part, which is to find out Fourier transform of given signal. But the next task is to find out or plot the spectrum for the given signal. So here we have two types of spectrums. First is amplitude spectrum and second is phase spectrum. So first let us start with the amplitude spectrum. So for amplitude spectrum, we need to find out mod of x of omega. So here we need to find out the magnitude of the given frequency representation equation, and then we can plot the spectrum. So here it is mod of 1 upon a plus j omega. So here we have the given term in complex representation a plus j omega, but it is a denominator. So first we have to separate out real term and imaginary term, and then we can find out the mod. So let us first simplify this x of omega term. So let's say x of omega was given as 1 upon a plus j omega. So now I need to separate out real and imaginary term. So make use of rationalization. Rationalization means we are going to multiply and divide this answer with the complex conjugate of this term, which is a plus j omega. So here it will be multiplied and divided by a minus j omega upon a minus j omega. So if we multiply and divide it with a minus j omega, at numerator we are going to get the term as a minus j omega divided by, so it is a plus b and a minus b. So it is a square minus b square. So if we simplify it, we get the term as a minus j omega divided by a square plus omega square, because j square is minus 1, so minus of minus becomes plus, so denominator term becomes a plus omega square. And now we can represent this term into real and imaginary parts. So our x of omega is equal to, real term becomes a upon a square plus omega square minus j into omega upon a square plus omega square. And now we can find out the mod of x of omega. So here mod of x of omega is nothing but a real term square plus imaginary term square. So it is under root of a real term square plus imaginary term square, so which is nothing but a upon a square plus omega square whole square plus omega upon a square plus omega square whole square. So if we further simplify it, So we get under root of, so here we can separate out the square terms. So here a square upon a square plus omega square square plus omega upon, it is omega square upon a square plus omega square square. So we can now add the numerator terms because denominators are same. So we get under root of a square plus omega square divided by a square plus omega square square. So now here we can cancel out the numerator with the square of denominator. So our answer is 1 upon under root of a square plus omega square. So this is mod of x of omega. So using this equation we can plot the amplitude spectrum. Now see how to plot this amplitude spectrum. Here for different values of omega we need to find out the magnitude x of omega. So let us prepare a table. Here we have values of omega and mod of x of omega. So let us assume a range of omega. Let us see, say it is from -5 to +5. And here mod of x of omega, we are supposed to find out the values. So in mod of x of omega we have 1 upon mod of a square plus omega square. So in the denominator term we have a square. So we need to assume certain value of a square which will simplify our equation. So let's assume that a is equal to 1. Just for simplicity we can assume any value. There is no restriction that a should be 1. You can take any value of a. So here mod of x of omega now becomes 1 upon under root of 1 plus omega square. So if we put up the value of this omega in this equation, so omega is -5. If we put up those values, we get the value of x of omega at omega equal to -5 as 0.1961. Similarly, at -4 we get value as 0.2425. At -3 we get value as 0.3162. At -2 we get value as 0.4472. At -1 we get value as 0.7071. At 0 we get value as 1. Now see, once we find out the value for this -5 to 0, for 1 to 5 again these values are going to repeat. So these values will be 0.7071. At 2 it will be 0.4472. At 3 it will be 0.3162. At 4 it will be 0.2425. At 5 it will be 0.1961. And now we need to plot the amplitude spectrum. So this spectrum will be omega versus mod of x of omega. So we'll plot the values from -5 to +5. So if we plot the values, so at 0 we have value as 1. So let's say here somewhere I have amplitude as 1. Then at 1 and minus 1 value is 0.7. So 0.7 is somewhat less than 1. So it will be somewhere here. Then at minus 2 and plus 2 we have value 0.44. So it will be down somewhere here. Then at minus 3 it is 0.3. So value will be somewhat lower than it. At 4 and minus 4 it is 0.24. So it will be somewhere here. At 5 it is 0.1. So it will be here somewhere. So if we plot the spectrum, you will get the nature of spectrum in this way. So in this way we have plotted the amplitude spectrum for the given signal. So this is your amplitude spectrum. Do not forget to mention the name amplitude, or it is also called as magnitude spectrum. Now similarly we are supposed to find out the phase spectrum. So for phase spectrum we have angle of x of omega equal to tan inverse of imaginary part divided by real part. So from above equation we have simplified the x of omega, and we know that the real part and imaginary part are given as by this equation. So real part is a upon a square plus omega square, and imaginary part is minus j omega upon a square plus omega square. So put up these values in this equation, we get tan inverse of imaginary part is minus of omega divided by a square plus omega square whole divided by real part is a upon a square plus omega square. So here this a square omega square gets cancelled out, and we get the equation as tan inverse of minus omega by a. So again we are supposed to prepare a table and find values of angle for x of omega for different values of omega. So this is our angle of x of omega. So for phase spectrum we have taken tan inverse of imaginary upon real term. We have substituted imaginary term as minus of omega upon a square plus omega square, a real term as a upon a square plus omega square, so it gets cancelled out, and we get angle of x of omega equal to tan inverse of minus omega by a. So again we are supposed to prepare a table for different values of omega and tan inverse of minus omega by a. Again we are supposed to assume certain constant value of a. So instead of preparing a new table, so let us mention these values of a in the previous table itself. So here I will add one more column. So first column is for different values of omega, second column is mod of x of omega for amplitude spectrum, and third column as angle of x of omega. So we have now to find out angle of x of omega, which is given as tan inverse of minus omega by a. But here let us assume a equal to 1. So it simply becomes tan inverse of minus omega. So here remember that you can find out the value of tan inverse of omega, where omega is minus 5, minus 4 up to plus 5, either in degrees or in radians. It doesn't make the difference. We are only interested in the nature of the graph. So here if we find out tan inverse of minus omega by a is 1 for omega equal to minus 5, we get the value as 1.37 34. For minus 4 we get the value as 1.3258. For minus 3 we get the value as 1.2490. For minus 2 we get the value as 1.1071. For minus 1 we get the value as 0.7853. For 0 we get value 0, and again these values are going to repeat, but here we have sign change, so it is 0.7853 minus 1.1071 minus 1.2490 minus 1.3258 minus 1.3734. So remember that in both the cases, in finding the magnitude as well as finding the angle, we get the values for negative omega equal to positive omega, but for magnitude the values are same, and but for angle the sign is changing for positive values of omega. So just cross check it and specify the values. No need to find out these values for every 1, 2, 3, 4, 5 of omega. Only find out it for minus 5 to 0 and replicate it in the positive values for omega. So now we are supposed to plot the frequency spectrum or the phase spectrum, which is drawn as omega versus angle of x of omega. So again mark the coordinates minus 1, minus 2, minus 3, minus 4, minus 5, 1, 2, 3, 4 and 5, and now plot the values. So at 0 we have 0 value, at 1 and minus 1 we have 0.78. So here we have 0, at 1 it is minus 0.78. So let's say we have the values as 1 and 2. .78. So for 1 it is minus, and for minus 1 it is plus 0.7. Next we have the value at 2, it is 1.1. So at 2 it is 1.1. Here also at minus 2 it is now 1.1. At 3 value is 1.2. So minus 3 it is positive value 1.2. At 3 it is negative value. Similarly at 4 and 5. So if we draw the graph, we get the nature of graph in this way. So this is the phase spectrum for the given example. So just to summarize, first of all, from the given equation, x of t was e raised to minus at u of t. We have used the formula of x of omega, integration minus infinity to plus infinity x of t into e raised to minus j omega t, which is the Fourier transform equation. We have substituted values of x of t, changed the limits of integration because of this unit step signal, then obtained x of omega, which was 1 upon a plus j omega. Then we are supposed to plot amplitude and phase spectrum. For amplitude spectrum we need to find out mod of x of omega. So we used rationalization to get real terms and imaginary terms into a separate way. So we got real term and imaginary term into separate slots. Then we have obtained mod of x of omega, which was 1 upon root of a square plus omega square. And then here we have assumed value of a and plotted value of mod of x of omega for different values of omega. So we have assumed it to be from minus 5 to plus 5, and we have plotted the values of mod of x of omega, and then we have plotted the spectrum. That is what the amplitude spectrum. Similarly, to find out phase spectrum, it is tan inverse of imaginary upon real value. So again we have substituted the values of imaginary term and real term in this equation, and again we have got the value of angle of x of omega as tan inverse of minus omega by a. So here in the same table, we have added one more column, angle of x of omega, which was tan inverse of minus omega by a. And here for simplicity, we have assumed a equal to 1 and plotted the values of tan inverse of minus omega for the range minus 5 to plus 5. And then again, we have plotted the graph omega versus more angle of x of omega. So this is our phase spectrum plot. So in this way, we can solve the example of Fourier transform.